It is my great pleasure to introduce Professor, please forgive me if I don't pronounce this well, Professor Rajendra Acharya. Very bad, I'm sorry. Is a professor at University of Southern Queensland. He has published over 600 papers and authored more than 17 books in biomedical imaging, signal processing, and data mining. He has received cumulative grants exceeding 6 million Singaporean dollars and has been ranked in the top 1% of highly cited researchers in computer science for the past 7 years. So please join me in welcoming Raj.
Okay, thank you, Suzanne. Let me share my screen. Just give me 2 minutes. Okay, good morning, everybody. The title of my presentation is Application of AI Techniques in Cardiology. So I'm going to share the results of these 3 projects. Then I will just, briefly discuss about the challenges and the future directions. So the first project is application of higher order spectra for the characterization of coronary artery disease using ECG signals. So as we know that the cardiovascular diseases are the #1 cause of death globally. So it's projected to rise 22.2 million by 2030. So it's caused by atherosclerosis, and it's basically the narrowing and hardening of arteries. So formation of plaque as a response to injury to the endothelium of the arteries, different arteries. So the standard methods of diagnosis are, cardiac catheterization, wherein the catheter is inserted into the arteries, and, coronary calcium scan, that is using CT, the echocardiogram, exercise stress test, that's TMT, and ECG. So these are the different modalities that's been used. So in this work, we have used ECG signals. So the proposed method is something like this. So what we have done is we have taken the ECG signal, then we have detected the QRS detection, then we have computed higher order spectra, which I will discuss later. Then we have done principal component analysis, that is PCA, and then we have done the classification. So in between, we have done the feature ranking also. So for this work, we have taken the ECG signals from the PhysioNet. So St. Petersburg, this is the database, and we have from here we have taken the CAT 7 subjects, and from the Fantasia database we have taken the normal subjects, that is 42. So as you can see here, we have totally taken 182,000 ECG beats for this study. So first we have done the pre-processing. We have done, we have done the resampling because 2 classes are having different sampling rates. So we resample them, to make the same sampling frequency. Then we removed the baseline vendor, and we also removed the noise. And then we have detected the R peak. Then we have taken 64 samples before the R peak and 104 samples after the R peak. So that is how we obtained the normal and CAD ECG bits. So now I will briefly tell you about the higher order spectra. So these are the EEG signals, not ECG, brain signals. So this is the normal brain. This is background just before the seizure, and it is during the seizure. So if we take the FFT of this fast Fourier transformation, so it looks like this. All the EEG, they look almost the same. So it's very difficult to discriminate them. So if we do higher order spectra, that's basically what we have done is we have taken 256 points FFT. We take the FFT signal. Then we have done the bispectrum. Bispectrum is basically this formula, x of b of f1, f2, x of f1, x of f2 into x conjugate of f1 plus f2. So it's a third order statistics. So f1 is this and f2 is this. So you give different values for f1 and f2. So we get this bispectrum. Then we have taken another bispectrum with 128 points overlapping. So you take another 256 points and you get another bispectrum. Like this, we get many bispectrums. You take the average of that. That is what we get, bispectrum. So this is the average of that. So like if you same EEG signal, you take normal, background and seizure, you will get this pattern. So we get the unique pattern. So we can use this pattern to discriminate to further classification. That's what exactly we have done. Now coming back to our normal and coronary artery disease, this is the normal bispectrum for the normals class, and this is for the coronary artery disease class. As you can see, they are very different. And we have also done higher order cumulants, actually, which I will discuss later. The cumulant, this is for the normal class, and this is for the coronary artery disease class. So higher order spectra is basically non-linear in nature because it's having third order. So, and also high signal to noise ratio. So it's able to capture the, interaction between the frequencies. So these are the, equations for the cumulants. I think you can refer this paper for the cumulants. And after getting these patterns, what we have done is we have done principal component analysis. Basically, it is the data reduction technique, which you know. And these are the features we have obtained for the bispectrum and HOS cumulants. These are the principal components. So what is so special about this is what we have done is, these are the principal components for the bispectrum, and these are, principal components for the cumulants. We came out with this equation. This equation, we, by trial and error method, we found out. And BI1 is the first principal component of the bispectrum, and BI2 is the second. So we put these values within this equation, and what happens is we get this range. This is the range for the normal class, and this is the range for the coronary artery disease. As you can see, they are very clearly distinguishable. So you don't need to have a classifier per se, you just need to put these values, BI1 and BI2. So they are able to classify. So this is an index, and this is totally new, and similarly, we have done this for the cumulants also. As you can see, they are very well distinguishable. So we don't need a classifier. You just find out the this BI1 and BI2 values and put it in this equation, so they are able to classify them. Of course, we have also done using the classifier. Using the classifier also we have done. It's close to 100%. So this is the novelty of this work, and this is published in Biomedical Signal Processing and Controls. The second work is the coronary, same database using CNN. We have used a, deep learning model, same database, but only thing is here we have taken 2 seconds of data. We have also taken 5 seconds of data. Just want to, touch on the CNN, the working of this. It has got 3 layers. In the convolution layer, pooling layer, and fully connected layer. In the convolution layer, you take the data, and we take the kernel. You just multiply the the values of the kernel and the data. So we get this. So this is the data. This is the output of the convolution layer. We get these values. So it's basically what it does is it's able to pick up the subtle changes, the spatial informations present in the data. Then the next layer is the max pooling layer. So we take the data here, actually, 2 data, you take the maximum, and between these two, you take the maximum. Between these two, you take the maximum. This is the output of the pooling. So what it does is it reduces the dimension of the data. The finally, actually, fully connected layer. In the fully connected layer, what happens is, the output of this, and you multiply by the weights, and we give some values to the weights here, and you get the output 82 and 86. Then, and after this, we can use a softmax layer for the classification. So this is the CNN structure we got for 2 seconds of data and 5 seconds of data. As you can see, actually, the model is not huge. It's a simple model. It's able to classify, and this is the classification result of, for 2 seconds and 5 seconds. The third project that we have done is explainable AI technique for ADHD and conduct disorder using ECG signals. So, as we know that the ADHD is basically, people, children having attention deficit. This work we have done in collaboration with Institute of Mental Health, Singapore. So, like they have attention deficit problem, impulsive nature, hyperactivity, like that. Then conduct disorder is basically, like children are having, they'll be cruel, vandalism, delinquency, all this. So, like here, the important thing is we have taken the 123 children data we have taken with 45 conduct disorder, 62 ADHD and conduct disorder, and 16 only conduct disorder. Usually, such children, they have, comorbid conditions. So what we have done is we have taken 2 seconds of data, we fed into the CNN model, and we have done the classification of ADHD plus conduct disorder and conduct disorder. And here we have also done explainable AI, which I will discuss later. So this is the deep learning model we have obtained, like for the 3 classes. As you can see, the model is also, like small. And this is the tenfold cross-validation results we have obtained. The accuracy is pretty good. And this is the confusion matrix, and this is the accuracy curve, and this is the model loss that we have obtained. Actually, from here, actually, you can see that the model is pretty good. What is so special about this? So the thing is, usually, like when we say that the mental problem in children or in human beings, usually we use EEG signals. And this is in this work, what we have done is we have used ECG signals. Instead of EEG data, we have used ECG signals. So this is the totally novelty of this. It's mainly because brain-heart interactions are largely mediated by the autonomic nervous system in healthy as well as diseased patients. And as you can see, actually, we have published one paper in this Computers in Biology and Medicine. And here what we have done is, here we have used CNN model, deep learning model. To the best of my knowledge, we are the first group to use this CNN model for this data. So what we have done is we have also used the explainable AI. So the explainable AI means actually, like it's usually all these deep learning models and machine learning models are black boxes. So the clinicians won't be convinced about this, like when we say that our result is, 96% like that. So they may not be able to convince. So what we have done is, in order to convince them, actually, what we have done is we have implemented explainable AI. That is, we have taken the model and all the data except one subject per class, all the other data we have used to train the model. Only one subject, that in that one subject, 2 seconds data we have used to test the model. So after testing the model, we have used GradCam, that is explainable AI function. And as you can see here, for ADHD, we are able to get this type of, like signatures. As you can see, this is for ADHD class. And for ADHD plus conduct disorder, actually, we are getting this type of signatures, visuals, like, and for conduct disorder, we are getting this. So that means these are, like the model developed this. So that means model is learning the classes. So this is the novelty of this. So this can be used to convince the clinicians. This is what we have proposing. The challenges, actually, after having done these 3 projects, like I feel that the challenges that we faced are more, we need more data. For example, in our first work in our coronary artery disease, we have taken only 7 subjects because those are the maximum subjects available in the PhysioNet, and 40 for the normal class. So it's very difficult to develop a very robust generalized model. So we need more data. I think this is the challenge we are facing. The second problem that I foresee is the data imbalance. Most of the times it's highly imbalanced. The disease class will have less number of subjects as compared to the normal. Then actually, like we need to, new deep learning models can be developed to handle data imbalance problem. Then hardware is an issue. When the data becomes more and more, then actually computationally intensive, it becomes computationally intensive. So we need GPUs, which are expensive. And I strongly feel that there should be more public databases available for all the diseases. And lack of standardization. This is another challenge that we are facing, because most of the times authors, they don't, sometimes sometimes, sorry, they don't report the accuracy. Sometimes they report accuracy, they don't report sensitivity, specificity, and area under the curve like that. So it becomes a bit difficult to validate our results with other author results. So actually there should be a lack of, there should be standardization in reporting the results. The future work is, I feel that there should be we should focus more on the early detection part. For example, early detection of coronary artery disease or congestive heart failure, all these things. So the early detection helps to save the life and to give accurate treatment at the right time. And also it saves the cost. Then, as I told, actually explainable AI, I think it can be used to convince the clinicians. Otherwise, whatever work we are doing, it may not go to the hospitals. For example, like in the explainable AI here, actually, we can always say that which feature is very important and which feature gives maximum performance. For example, like glucose, or like a blood pressure, something like that. Like we can see which feature is contributing maximum for the performance. Then like this is one of the works that I have done. I thought I'll just share with you. Like in the explainable AI, for example, this is the kidney stone. So actually this is the kidney stone, and if we can say that, hey, this is the place where like the kidney stone is there. If we can show it to the clinicians, okay, this is the thing. This is the heat map which is generated by the like explainable AI. So if we can show those lesions or something like that, then actually it can convince the clinicians. The other thing is the uncertainty. So I feel that whatever models that we have developed, like it's developed under, like ideal condition, that is without noise and all those things. But if when we install these models in the home-based environment and in the actual ICUs, these models may not perform very well because they are always subjected to baseline wonder, noise, all these things. So these models may not perform very well. So we need to also take uncertainty into consideration. We need to quantify the uncertainty and we need to address them. So then only our models will work. So that is the other issue. Then the other thing is information fusion. Maybe we can fuse the information, ECG plus MRI, the image, or ECG plus image. We can fuse and we can get accurate results. That is also the other thing. Then more classes can be added. For example, in my presentation today, I have done normal and CAD. Maybe we can do normal, CAD, MI, myocardial infarction, maybe congestive heart failure, all these. More classes can be added. Then the other thing is, like we can also detect mental health using ECG signals instead of EEG, because EEG is highly noisy. More channels are needed. Maybe we can go for ECG, and also heart rate variability or PPG. From PPG, we can get heart rate variability, and from the heart rate variability, we can detect different mental disorders. Sorry, mental, physical as well as cardiac as well as mental disorders. I think this is what I feel, because using heart rate variability, the bandwidth will be significantly reduced. So as a result, actually, like we can use it in mobile phones and all those things, or in the home-based environment. Yeah, I think this is the end of my presentation. Thank you very much for the opportunity.
Excellent. Thank you so much. Fascinating work. Do we have questions from the audience? I was wondering, could you paint a picture for us how you see your work implemented to the bedside of the patient, really?
Oh, okay. Yeah. Okay. You're asking me the question, right?
Yeah.
Okay. I feel actually, to me, I think these works are, like I am more keen on implementing the work related to the ADHD conduct disorder, this one, because this is where my focus is now, because I feel that if we can, this is how I see the future. I see that actually if we can detect the PPG signal from the PPG, as we know, PPG can be easily captured, easily obtained, acquired. Using the PPG, we can get the heart rate variability, and from the heart rate variability, maybe we can detect ADHD conduct disorder and other mental related issues. So I feel that this can be implemented. Of course, actually, the data is a big problem, and I'm working closely with the Institute of Mental Health Singapore to pursue this work. Yeah, I think if any of you are, like happy to, collaborate with me, I'm happy to join. I'm happy to proceed. Yeah, this is my answer.
Great, fascinating. One question from the floor, from Lewis.
I'm curious that you're looking at the heart signals, brain signals, and you're looking at them separately. Could you potentially gain something, and I'll put out there that this is not my space, by incorporating those models together in a model? Is there potential extra information by looking at the two of those sets of signals?
I'm sorry, could you repeat the question? I'm sorry.
On.
Okay, so from my understanding, you're looking at just the heart signals, but there are obviously also brain signals that have been looked at in a similar fashion. Do you gain something by looking at both sets of signals together? Does that give you another level of information that would not be available otherwise?
Oh yeah, this is an excellent question. Beautiful question. Yeah. Okay. Now I just want to tell you that using the, I just wanted to say that using ECG alone, we can detect, different mental disorders. That is what I have presented here, because there is a like brain heart interaction is there, mediated by the autonomic nervous system. As we know, actually, like when I'm tensed, actually my heart beats faster. When I'm relaxed, my heart will be more relaxed, something like that. Now, the point is here in this work, I presented that using ECG, we can detect different mental disorders. Yes. Now, answering your question, using ECG as well as EEG, brain signal, can we get more information? Yes, definitely yes. You may ask me what information extra you can get. See, using EEG, we have different channels. So we know at which region of the brain is having problem. Using ECG, we cannot say which region of the heart is, which region of the brain is having problem. It will tell you whether it is ADHD, conduct disorder, or something like that. But if we can fuse EEG also, it will give additional information. It will tell you which region of the brain is having problem in addition to the class. Maybe I think what you say is correct. It's a information fusion. We get more information. Maybe we can get accurate results. Yeah, good point. Yeah, thanks. Did I answer your question? Did I answer your question?
Absolutely. Great.
Yeah, thank you.
Okay, do we have any other questions? Virtual question. Sunit was asking, how can we interpret grand CAM result on third work? Is the pattern consistent on all test samples for 3 classes?
Yeah, yes. Actually, we did actually obtain most of the cases. We get this type of patterns, like this type of pattern. Actually, what we have done here is we have used, actually there are 123 subjects are there. 122 we used to train the model, and one subject we took it as a test sample, and in that one subject we have taken 85 chunks of data. That is 2 seconds of 85 chunks of data we have used to test, and we implemented GradCam, and we obtained this type of things. Actually, the more or less, actually the trend is similar. Yeah, we get.
Thank you. One more question from Halua. Have you come across a method or paper that has biased a CNN towards early detection?
Say again, actually, could you?
Have you come across a method or paper that has biased a CNN towards early detection?
No. Actually, I did not I did not come across this type of things. Actually, like biasing, no, not really. I did not come across early detection, because I think to me the problem is it that the problem is the data. Early detection of the coronary artery disease or MI is the data. Actually, we are unable to get the data. I think that's why I did not come across any paper like that so far.
Okay, great. I think that concludes all the questions. Thank you so much once again. Excellent.